So good afternoon, everyone. I think it would be appropriate to start our seminar with a moment of silence, and because of the loss of our colleague, of the former professor working at the Astronomical Observatory of University of Warsaw, who passed away a few days ago. So just silence. Thank you very much. And with that, I would like to invite our speaker to today's seminar, Malgorzata Curylo, who is a PhD candidate at our observatory, and who will tell us about the massive black hole binaries as a tracer of multi-messenger studies, physical studies. Malgorzata, the floor is yours.
Okay, hello everyone here and online. So yes, as the introduction says, I'd like to talk about massive black hole binaries and how we can study them using their multi-messenger signatures. I would like to go further. That doesn't work. That works. Okay, thank you. Okay, so massive black holes are the objects of masses larger than 10 to 4 solar masses, and they reside in the centers of both large and dwarf galaxies. We also have many observations that indicate that they co-evolve with the host galaxies. We see many relations between the masses of massive black holes and many ranges and scales of properties of galaxies, like stellar masses, luminosity, and we also see the relation between AGN and stellar star formation rates. What's most important for me and what I would like to talk about is that massive black holes also form binaries. But this looks beautiful, but we have many observations, but still we have very little knowledge about them. First of all, there are some problems with the relations themselves. They are different for different systems. We have very poor and little data above redshift 6. So basically everything what we know is based on the local universe. Most importantly, closed binaries are not resolved. And the basic astrophysical questions are how do these massive black holes form and evolve together with the host galaxies. So we have a few ideas of the formation and growth models. The basic problem here is that the evolution starts very early in the universe. So when the first stars and first galaxies started to be born, and this is where we cannot look with our telescopes. So the most popular ideas, the most popular scenarios involve either low, medium, or high mass seeds. The low mass seeds would be the population 3 stars, which after evolving, they will collapse to massive black hole seeds of 10 to 2 solar masses. A little bit higher masses of seeds would be generated from stars in nuclear clusters, a little bit more evolved stars, but still at the very early ages in the cosmic history. And due to very high densities in these nuclear clusters, they interact with each other a lot and merge, and that's why we can get higher masses of black hole seeds. The last scenario involves a direct collapse of a gas cloud, which would generate a seed of 10 to 5 solar masses, which is a lot. But the main problem here is that the direct collapse scenario involves very specific conditions that need to be met. So that's why we can, of course, we can get a very massive star, a massive black hole at the beginning. However, if they happen at all, they will be very rare. On contrary, massive black holes from population 3 stars should be abundant, should form frequently. However, their masses are really, really low, 10 to 10 solar masses, 10 to 2 solar masses. And it's really hard to explain how could they grow several orders of magnitude in very short time to form quasars at redshifts over 7, which have masses 10 to 9 and 10 to 10 solar masses. So the growth of massive black holes comes with accretion and mergers, and to have mergers, we need to have binaries. So how do these binaries form? We believe that they form during galaxy mergers when the two galaxies have black holes in the centers. The merger of galaxies will lead to the formation of some remnant galaxy in which two massive black holes will sink to the center via dynamical friction. When they reach separations of about a few parsecs, we would see the formation of the gravitationally bound binary. Right now we have only one single observation confirmed of a binary that close at around 7 parsecs. If they effectively shrink even further to subparsec separations, we know that they would generate gravitational waves, which would bring them to merger in relatively short time. But the main problem is this very last stage before gravitational emission. We do not know much about this because we have only one observation at this separation. We have no idea if they actually get closer together. There are some studies that say that stellar and gas interactions are not enough to bring massive black holes even closer together, and this is called the final parsec problem. So I would like to talk about this a little bit more in future slides. Each of the stages is related to, or can be related to, some electromagnetic emission. For example, we can see dual AGNs when we have in X-rays or in radio, we have both cores visible, like in this picture. We can have AGN variability and some spectroscopic features related to the orbital motion. And also orbital motion can distort and make jets do weird stuff for black holes which emit jets, either one or two of them. The problem here is that none of the signatures is able to pinpoint the massive black hole binary by itself, because most of them can be related to some other phenomena. For example, even the direct image could be related to star formation regions. So we are not certain that these could be two black holes, in fact. So we need multiple methods simultaneously on one binary candidate in order to make a concurrent detection. That's why we have just a handful of them right now. What would be good to have would be to observe gravitational waves from them, because that would be the smoking gun of the binary, and it would tell us a lot about the system's evolution. And we would have a final confirmation that binaries actually go closer and do merge, and the final parsec problem is solved. the two main missions that work on detecting gravitational waves from supermassive black holes are pulsar timing arrays and LISA. So how do they work? So massive black holes are very different from stellar mass black holes, which are probed by terrestrial interferometers. And basically, when we go to lower masses, we probe higher masses, we probe lower frequencies, and we need our arms of the detector longer. So as the terrestrial telescopes have 4-kilometer arms, the LISA telescope will be orbiting in space and will have over 2 million kilometer arms. And in pulsar timing arrays, probing the lowest frequencies would have, they use the technique to observe pulsars, which are located hundreds of parsecs away from Earth. So we have even larger distances like this. So LISA is going to start, let's hope for this, in the late 30s. And we will be able to see the in-spiral and merger similarly to the terrestrial interferometers, but the signal will last for months and days before the merger. Whereas the pulsar timing arrays, well, they can probe individual in-spirals. However, they will be really buried in the signal. So what we expect to see first will be the sum of all the in-spirals that will give us the gravitational wave background of a given amplitude and spectral index. And actually, it seems that we are already seeing something in our... Sorry, I had to do this. We are actually starting to see something in our data. We have the first gravitational wave background evidence. This is still lower, the significance is still lower than 5 sigma. So we try not to say that this is the detection actually, but this is the first hint that we've been waiting for over 20 years. So what we get from gravitational wave background here is the amplitude, and which we can compare with, for example, simulated and expected from simulated massive black hole binaries. However, it turns out that the gravitational background signal of this amplitude is consistent not only with gravitational waves from supermassive black holes, but also from other more exotic sources like cosmic strings or inflation in the first universe. So in order to find the source actually and say certainly say that this is not instrumental or this does not come from pulsars themselves, we need to look to our models and compare predictions from our models with the kind of signal, of course, apart from keeping our observations going, as we believe that the signal will be higher in amplitude, higher in significance, with adding more and more observational data. So how we try to compare the observations from pulsar timing arrays and simulation. So what we have done in our work was to use a galaxy evolution, formation evolution model, as black holes also evolve in the galaxies. And we took this particular shark model because it's an open source, it's very flexible, modular, we can add many different models, and this is really a community code that caught our eye. It was tested with different observational constraints, and it does a really good job in this. The basic problem with most of such simulations and models is that they treat massive black holes very simplistically. These are just point sources that merge immediately after the merger of galaxies. But as I just showed you in the previous slides, the evolution of the binary within galaxy merger remnants is quite long and difficult process. So what we have done was to take the output of the simulations and treated this as a initial massive black hole binary population, and we added specific models of binary evolution to the massive black hole, to assess what happens to them after the merger of the galaxies. when they travel from kiloparsec to subparsec separations and finally merge. So the first process from the very distant separations is the dynamical friction, as I mentioned before, and the process is depends on the initial separation of massive black holes, the velocity dispersion of galaxy, masses of black holes that sink inside. And when we calculated the time scale between the time scale of dynamical friction between the merger of galaxies and the formation of the bound binary, we will find that only 40% of galaxy mergers will result in the formation of a gravitationally bound binary in less than the Hubble time. Most importantly, the least massive black holes, which are still massive, 10 to 5, 10 to 6 solar masses, have less chances to make it to the binary because of the how dynamical friction works. So then, when we have our binaries, we can further evolve them to subparsec separations when they start to evolve gravitational waves. And these processes depend on whether there is a lot of gas in the galaxies or there is not a lot of gas. So when there is not a lot of gas, the binary will interact only with stellar contents. So whenever there is a star nearby the galaxy, it will interact with the galaxy, and via the distinction effect, it will take out the angular momentum, the orbital energy from the binary, and make the binary shrink even further. So this depends on the density of stars in the vicinity, basically in the vicinity of the binary. In case of gas-rich galaxies, around the binary we will have a gas disk, and the binary will interact with the gas disk, and the viscous drag from the disk will make the binary shrink further. And after we include all of these timescales, when we add them up together, we will see that only 22% from all galaxy mergers that we considered will actually merge before redshift 0. This is very important because most of the simulations of galaxies, they study galaxies which are affected by black holes feedback, for example. However, they assume that all of them merge inside the galaxy, and they reach the centers of galaxies, which apparently is not true. So the binary lifetimes, as understood from the merger of galaxies until the merger of black holes, is of the order of a few gigayears, and we can see that the gas evolution is more efficient in bringing the binary close together. The binaries are evolving faster with gas content in the galaxy. And what we can now do, we know how many binaries reach the gravitational wave emission. We can calculate how much gravitational waves they will emit, what will be the amplitude of the gravitational waves, and we can compare this to the observations we get from pulsar time arrays. And here on this plot, you can see with the black lines, the amplitude of the gravitational wave background, the signal actually, detected by the pulsar timing arrays. And in the color lines, you can see what is simulated. The topmost line, the purple line, is showing you the most optimistic scenario, which involves all massive black holes merge immediately after the merger of the galaxies. Whereas the green one shows you what happens if we add all of these processes that delay the merger of massive black holes with different colors showing you gas poor and gas rich galaxies. So what you can see basically from this is that two things. First thing is that the delay mechanisms make very small difference when compared to analyzing all of the massive black holes. This comes from the fact that only 11% significantly contribute to the gravitational background. So only those which are the most massive, more than 10 to 8 solar masses, and at relatively low redshifts, about up to redshift 2. And the second most important thing is that the signal simulated is lower than the signal detected by the PTAs. And now the question is whether is that the observations are observing something else than the gravitational background from supermassive black holes, or our simulations are treating, maybe we don't understand galaxies and massive black holes. We don't analyze them in a correct way. So answering that question will actually take at least a few more years. And there is a lot of discussion and debate in the community about this right now, because many other works also predict something similar. So we need more time to answer the question. And here in the last part of the presentation, I would like to get back to the electromagnetic signatures, which can be related to supermassive black hole binaries. And specifically, I would like to focus on the jet morphologies, which are not very talked about, which are not talked about very often. So here you can see an example of such a jet morphology, which is distorted, peculiar. This comes from the X-shaped radio galaxies, and the name comes from the characteristic shape of the two lobes, primary and secondary, making this shape. So just a few characteristic properties of such sources is that they constitute relatively a low number of all radio loud AGNs, but interestingly, they have more massive black holes inside them and older starburst activities. And there are several ideas how to solve the problem, because we still don't know what is the actual source of this kind of shape. And why am I actually telling you about this is that because there are several ideas that link this shape to massive black hole binaries. So one of them is, the first of them would be that we have an unresolved binary inside the radio galaxy, which where the two black holes emit jets at the same time. So we can see that the jets are mesolites. The other scenario is that we have only one black hole inside. However, there was a binary before, which where one of the black holes had a jet, and then after the binary merged, the jet changed suddenly its direction. That's why the secondary lobes would show us the direction of the old jet, and the primary lobes would show us the jet where the jet is right now. Some of the properties of these sources show that this kind of scenario is likely to happen, for example, because of the larger masses of black holes or older starburst activities, which could indicate that there was a merger in the system happening before. So when we have our populations of massive black holes from the simulations, we can make a fun experiment and see whether we can reproduce from our binary massive black holes, reproduce any kind of any sources like this to have X-shaped radio galaxies from our sources. So first we have to assume which massive black holes generate jets in our sample. And we used a few conditions for that. For example, the jets will be produced only the most massive black holes with slow accretion rates, because we can see in the data that the higher accretion rates mean lower radioactivity, and the black holes would be more quasar-like instead of emitting jets and creating these beautiful lobes. And some optical spectra, like low excitation radio galaxies, which emit in radio mode, so they have small accretion rates, and they have also more massive black holes. In case of duals, we have another condition. Then the dual needs even more gas in the system. So we take into account only the gas-rich galaxies and higher mass ratios, so that our smaller black hole doesn't lose its accretion disk through the whole evolution process. So we have considered the two scenarios. We have either one jet which is suddenly changing its direction, or we have dual jets which are emitted in the same time. We can see that the dual jets are characterized with higher black hole masses, and they are produced at slightly smaller redshifts because they just need more time to grow this kind of big mass. Mass ratios are also higher for dual jets even before applying the gas-rich cut, which tells us the simulations themselves are making a good job in predicting this kind of emission. So first, what we have done was to, when we have our jetted massive black holes chosen, we assign them random spin directions and then calculated the angles that the final massive black hole would have after the merger. And we can see that the angles, flip angles, as we call them, after the merger, would be clustered around 30 to 60 degrees, which is actually consistent with the observations where exergs are observed also with this in this kind of range. In the case of luminosity and redshift distributions, we can see that the observations are consistent with the simulated objects, both the dual jets and single objects. We can see a lot of them being below the current threshold for our observational capabilities. So maybe when there are more sensitive radio observations, if they could spot these kind of sources below 10 millijansky fluxes. It is not seen in this plot, but making a simple statistical test showed us that the poor galaxies which have spin flips reproduce the observed population in the most favorable way. Okay, so this is my summary. I told you about how we can study massive black holes, what tools we have in our electromagnetic and gravitational spectrum. There are many unanswered questions, and but the detection of gravitational waves will actually help us answer many of those questions. And we have already got exciting results from pulsar timing arrays, and we are really awaiting for LISA, which will probe a little bit smaller black holes, but show us the evolution up to the most massive ones seen through pulsar timing arrays. I showed you that we have a problem explaining the signal detected by pulsar timing arrays. This would need a lot of more studies, but these studies will be really exciting to pursue. As it comes to electromagnetic signatures, we have studied the very peculiar and rare X-shaped radio galaxies, and we have tested two scenarios that relate them with supermassive black hole binaries. And actually, it turns out that they might be related to PTA-like sources. That means that they come from gas-poor galaxies. They have the most massive black holes, and they reside on quite low redshifts. Maybe it was here shown. They reside in a quite low redshifts. The highest observed exerg is up to 2.5 redshifts. So this can relate them to pulsar timing, which makes a lot more room for more multi-messenger studies. And our studies have shown that the spin flip scenario in the gas-poor mergers reproduces the observed properties of X-shaped radio galaxies well, in terms of redshift distribution, luminosity distribution, and also the flip angles. We could reproduce the flip angles. Thank you for your attention.
Thank you, Gosia. Do we have any questions or comments, concerns? Radek?
Can you go back to the slide with primary and secondary jets? Illustration.
Yeah.
So what the colors show? I understand it's some radio data, but
Yeah, that's
what exactly?
I think that's intensity of radio emission.
Is it neutral?
Like brightness. I'm not sure.
It's some radio astronomers. So, may I argue?
No, I'm thinking, but if there's any question, I could just.
It's actually, I have a question. I don't know if I understood it correctly. So, what's the correlation in between, like, okay, if we have like an angle in between one, let's say, jets and the other jet, or how do we call it? Is it somehow correlated with the spin of the merger?
Yeah. Because if we assume that the jets are produced when the black hole has an accretion disk, and the jets would be aligned with the spin of the massive black hole.
Okay.
So if they merge, the spin changes the jet.
Makes sense. Good. I was missing this one graphics in my mind.
Okay.
Any more questions?
Chris, if I may ask a very naive question. So if you have those two binary black holes that form during a merger, presumably their spin axes are not aligned either with themselves or with the orbit. So if I look at the jet from such a galaxy, in which direction would it go?
Well, the jets will be produced in both ways. So
What?
in both ways. Like when you have a accretion disk, the jets are usually both-sided. Like we have jets from the black hole up and down.
Two spin axes, and then there is the angular momentum of the disk, which is, so there are three directions. Which two are you talking about?
I'm confused now. I mean, the black hole is inside, and the jet is like.
But there are two black holes, right?
Yeah. So we have one, like in here are black holes, so they can be.
So we assume that the jets are along the spin axis of black hole.
Yeah.
And then the spin of the momentum of the disk is not related to the jet direction.
Okay, so when you talk about the spin flip,
The spin flip, when the black hole has a spin in a specific direction, when it merges with another black hole, the remnant black hole that comes up from this kind of merger, will have a spin directed in some direction. And if in the spin flip scenario before the merger, we assume that we have only one black hole with one spin. So we would the jet would be pointing in some point, and after the merger, it would change the direction because of the change of the spin of the black hole.
yeah, there are two black holes, right?
First, two. After the merger, we have one, which presumes the jet. The jet is not broken, but it changes the direction.
Okay.
So assuming, based on your simulations, and assuming that PTA astronomy keeps on developing, what would be your bet for the first binary black hole detected as an individual source? What masses will it have and what distance will it have?
Given that the masses should be above 10 to 9, 10 to around 10 to 10 solar masses. Consider the massive black holes of just the 10 to 8 solar masses. We don't even see them in the gravitational background. And in order to make them pop up, they would have to have much more masses. And in terms of the distance, the current searches show that that we don't see any individual massive black holes anywhere close to the distance to the Virgo cluster, the massive black holes of around 10 to 9 solar masses. So it should be above these masses.
I was wondering about the technological side, let's say. So you said, okay, we have now PTA and it's waiting for Lisa, but it's still like 15 years at least. And are there any advances in the industry, in PTA, or like technological advances that can be done to enrich the studies in the meantime? Or we are like
No, we are not in the limits. Currently, for pulsar time arrays, for example, we observe just 80 pulsars. This is really not a lot. And pulsar time array sensitivity to gravitational waves will increase with the number of pulsars because we will probe the sky better. And we have new radio telescopes being designed, like SKA in Australia and South Africa. They will detect many more pulsars so that we can add them to our surveys. We are upgrading our telescopes too, because the sensitivity of telescopes is very important. So, for example, we're implementing wide bands to have and of course the analysis tools to need to be understood better. There are some studies that show that the gravitational background that we're seeing the signal could actually come from some problems with our understanding of the statistical tools that we use, or they can come from pulsars themselves. So what would be really helpful would be to understand pulsars better and the emission mechanisms, because they add a lot of noise which we have to subtract in order to make the observations of this kind of very small signal.
And is this big fast China telescope somehow used in this? And see any more questions from here? Do we have anyone on Zoom?
Oh. Don't see any more questions. Okay, so if not, again, thank you.
And see you next week at the last seminar of the semester with Martin. See you. Thank you.